I hope you all had a very good Thanksgiving. And so, what I wanted to do was to give a couple of sort of short demonstrations about how one can use Bernoulli's equation or Bernoulli's law to sort of understand a number of different things. So, remember that Bernoulli's law basically says that the pressure plus the kinetic energy plus the potential energy is a constant. And so what we wanted to do is let's take a couple different examples about how one can understand that. If you talk about something simple like taking a straw and putting it into water, this one's sort of nicely transparent so you can see it, and then put your thumb over the top, what you know, I think everybody can see that. If you'll notice that the right there is the level of the water, and so it'll stay there perfectly fine. So there's the bottom of the tube, and the water is just being supported. If I, of course, release my thumb, then that basically allows the water to go down again. Okay, and basically it's gone. So let's do it again. So you can see the level of the water. Hopefully, about right there. Right there. And if I release my thumb, then it just falls out. Okay, and so everybody knows that that's the case. And so the question is, well, what exactly is happening in that case? Well, we talked about this once before, is that if you talk about a tube where you've got your, you have your thumb across it, right? Then there's a level of the water, and so in sort of the interior of the water, it's going all the way down. You still have the weight. In other words, it still has a weight down. And so the question, well, what exactly does it? What's supporting it? The sum of the forces by Newton's first law have to be zero. And so down at the bottom, you still have atmospheric pressure. And so in order to make it balance, what you have to do is the pressure up on top has to be less than the pressure down below. And so up here, in principle, it could be a vacuum, but essentially is that this has to be lower than atmospheric pressure. The pressure has to be lower. And so the force pushing down it on the top has to be less than the force pushing up it at the bottom, and that exactly supports the weight. This is why we talked about it before. Now, if you talk about Bernoulli's law, then the same thing applies, right? Because everywhere the kinetic energy is zero. And so the idea is that down at the bottom you have atmospheric pressure, but as you go up into the water, the potential energy term has to go up. And so the only way to keep energy conservation in place, because the kinetic energy is always zero, is that the pressure has to go down as you go up and along the tube. And it decreases by exactly what's required in order to actually support the column of water. But here we're talking about in terms of energy conservation. Okay, so let's try another example, which we saw once before. And that is this tube where you blow air through it, and you have sort of liquid down here. But at this point, there's a constriction. And so if I blow through it, the air going through the pipe on top has to go faster because it's going through this constriction. And when it does, then the pressure inside that constriction has to decrease. So, let's see how I'm doing on time. Yeah, we have enough. So if I do this, the idea is that you've got a big pipe that goes through a constriction. It reduces the diameter of the pipe. And the point is if you talk about these two things, then if you have the velocity of the air going through the big pipe, then the velocity has to actually increase as it goes through the small pipe. So if you talk about the Bernoulli's equation down here, then what you have is that you've got P plus 1/2 rho v squared plus the potential energy term on the left side, and then you've got it on the right side. Now the idea is the height doesn't change, and so you can sort of ignore these two guys because they don't change. But the point is that the kinetic energy on the right side has to go up, and so there's no choice to conserve energy but the fact that the pressure has to go down in the, within the constriction. And so you apply some pressure here, it's going through at some speed. If the speed goes up, then the pressure has to go down. Okay. You get this most amazing case where you've got a air flowing out of a tube. I'm going to turn this on. You may not be able to hear this. So you've got air sort of flowing out of the tube. And so air is being rushing out. And it pushes the ping pong ball out. No question. But if I shove the ping pong ball in, then it actually will hold it stable until I release the airflow, and then eventually it just falls out again. So here you've got a real quandary, right? Because the ping pong ball basically is being supported even though the air comes rushing out around it. So why is that? Well, it's still Bernoulli's equation that's involved. And so the idea is that you've got air coming through here and it's going into this funnel. And then you've got the ping pong ball, which is sitting there. And so the idea is that the velocity comes through here, but when it reaches this constriction, because now basically what you've got is it's got to flow around the ping pong ball. And so what it amounts to is that the velocity has to suddenly increase. But again, the idea is that if you've got Bernoulli's equation, which is applying here, then if the pressure goes up, and if the kinetic energy goes up, then the pressure has to go down. And so what you have basically is low pressure in these regions. And you've got atmospheric pressure here, which is pushing up on the ball. And so the ball is in place because the pressure has to be lower where the air goes rushing around it. This is not really what you think about. So I'll probably do a little bit more on this in the next lecture.